All right, grade 12 chemistry. If you thought Hess's law was difficult, this is going to be a whole lot easier for you. This is called standard enthalpy of formation. So we're going to learn what a formation reaction is. We're going to learn what the enthalpy of formation is, and then we're going to do some practice problems. And you should be able to pick it up a lot faster than Hess's law. Getting into it, one benefit for Hess's law is that we can use it to find theoretical enthalpies of reaction. And one of the theoretical enthalpies that we really like to find is called the enthalpy of formation. So we're looking for a formation reaction. This is a new type of reaction you might not have heard of before. That type of reaction is a reaction that makes 1 mole of a compound from raw elements. So here's some great examples. Here's carbon, solid carbon, and hydrogen coming together to make methane. 1 mole of methane. So we want to go raw elements, 1 mole of the compound. So carbon, hydrogen makes methane. Carbon, oxygen makes CO2. 1 mole of CO2. Hydrogen and oxygen makes water. Note that I had to cut the oxygen in half because I want to make just 1 mole of water. It's important to make 1 mole because we're going to be multiplying this later, and if we have it set to make exactly 1 mole of the compound, it makes the multiplying and dividing a lot easier later. One important thing here is that the raw elements have to be in what we call standard state. So the hydrogen needs to be H2 as a gas, oxygen needs to be O2 as a gas, carbon needs to be solid, and specifically graphite as a solid. It's not going to be diamond or graphene or any of those. So that's a formation reaction. And the standard state, like, it has to be the form that it takes at 25 degrees Celsius and 100 kilopascals. So that's a standard temperature and pressure. I'm going to pause. I'm going to go back to the old note. I'll show you that some of the Hess's law reactions we did were actually to try to find a heat of formation. So back in the note from the previous video, this was the formation of NO2. You see it's N2 and 2 O2s making 2 NO2s. That's not a full heat of formation. We need to make 1 mole of it. So we're going to have to cut everything in half. But it would be half of an N2, 1 O2, and make 1 NO2. And here, half an N2, half an O2 making 1 NO would be the heat of formation of NO. So that's we've seen something like it before, and it's very useful to use Hess's law to determine heats of formation, and then we can use our heats of formation to solve other problems. Keeping in mind that formation reactions are forming exactly 1 mole of product, and they have to be from raw elements. Those are the only two things that are required. It has to be elements in standard form and 1 mole of the compound. Here are 4 reactions. Here's 4 reactions, and only one is a true formation. Let's explain why the others are not correct. So take some time to look at it. Here we have hydrogen and chlorine. We look to see if they're raw elements. They are, just hydrogen, just chlorine. Here we have silicon and fluorine, just silicon. Solid silicon, which silicon is solid in standard state. F2, gas, standard state. That's good. Here we run into a problem. Our first problem is that calcium oxide is not a raw element. That's already a compound. So that is a compound. That can't be a formation reaction. This is also a compound, so that can't be a formation reaction. So number 3 is out because of the compounds at the start. Down here, iron, standard state of iron is solid. Yeah. Phosphorus, standard state is solid. Sure. And oxygen here, we have an issue, right? We have an issue here. It is a raw element, but oxygen exists as O2, right? O2 gas. O2 gas. So that disqualifies oxygen because it needs to be O2. The standard state of oxygen is O2 at 25 degrees Celsius, 100 kPa. Right, 25 degrees Celsius, 100 kPa. So that one's out. So number 3 is out based on that. Number 2 is out based on that. Or number 4 is out based on that. We've got these guys. These are standard state. these are standard state. Let's look at what we're making. Here we're making 2 HCl. That's an issue, right? That's an issue. We want to make only 1 mole of the compound. So the 2, right? The 2 is bad. If we wanted to make this into a formation reaction, it would have to be 1/2 of an H2, half of an H2, plus 1/2 of Cl2, making an HCl. Gas form. Okay, and that's gas. And that's gas. All right, gas. So that would be the correct version of that, which leaves only this one, and this one is all good. This one is a correct heat of formation reaction. Right? It's got standard state silicon, standard state fluorine. Even though there's 2 of them, that's just what it takes to make SiF4. We don't care about the numbers on this side. As long as we're only making 1 mole, we're forming 1 mole. So SiF4, that is 1 mole, so that is a correct heat of formation reaction. That one is good. And that's how you identify a heat of formation reaction. That's what a heat of formation reaction means. Or that's what a formation reaction means. Let's talk about heats of formation. Right, let's talk about heats of formation. One of the things about this is it's a heat, right? It's an enthalpy of formation. It's how much energy goes in or comes out when we form it. And so here's a few. They are measured, these ones in particular are measured in kilocalories per mole. It's kind of an older unit of energy. Normally we'd go kilojoules per mole. But please note that the standard state of, if something's in standard state, hydrogen, oxygen, chlorine, bromine, carbon, and graphite, they have 0 heat of formation. This should make sense because they're already existing. They're already raw elements. So it doesn't take any energy to form them from raw elements. Meanwhile, water comes from hydrogen and oxygen. If you burn hydrogen and oxygen, you release energy, you make water. You make a certain amount of energy per mole of water that you make. So that's hydrogen and oxygen making water. Carbon dioxide releases even more, 94 kilocal per mole. So carbon and oxygen getting together make that. Methane releases energy. Sodium chloride releases energy when sodium meets salt. Sodium meets chlorine to make salt. Releases energy. And it's important to note that pure elements are defined, absolutely defined, having no heat of formation, right? So when you see just a single element, it's got 0 heat of formation, 0 kilojoules per mole as their heat of formation because they're already raw elements. There's no input needed to make them, right? And no output if you make them either. So most are just solids, monatomic solids. Hofbrinkel are diatomic in standard state, HOFBRINCL. That's what Hofbrinkel stands for. And then some weird ones are like S8 and P4, the standard states of sulfur and phosphorus. Sometimes you get some weird ones like that. Also note, bromine is liquid in standard state and iodine is solid in standard state, which is kind of neat. So yeah, big thing here is that the raw elements in standard state have 0 heat of formation. And here's some other ones. Here's some heats of formation that were measured from other for other things. You can see that some of them have a positive heat of formation, like acetylene here. You actually have to put in energy to make acetylene from carbon and hydrogen. Other ones have a negative heat of formation, like ethane. Ethane down here has a negative heat of formation. You'd release energy making ethane from carbon and hydrogen. And sucrose has a negative heat of formation. It's more often to have a negative one, but sometimes it's positive. So hydrogen iodide is an example of one with a positive heat of formation, and benzene has a positive heat of formation as well. So hydrogen iodide, going hydrogen plus iodine, making hydrogen iodide. 1 mole of this, you would have to put in 26 kilojoules per mole. So that's a table. These tables exist. You can look them up. This is the one from your textbook. There's a lot of different ones. So that's some heats of formation. And this is properly in kilojoules per mole. Right here, the water is minus 285.8 kilojoules per mole. Meanwhile, here it's about 4 times lower because kilocalories. It's 4 kilojoules about is a kilocalorie, 4.2. Yeah. So let's just jump into the practice problems with heats of formation. We're going to talk about using a heat of formation to predict an enthalpy of reaction. Right, so here's the beauty of heats of formation. We can use them to predict a delta H. Right, remember, Hess's law says that the mechanism doesn't impact delta H. It doesn't matter what kind of steps you go through as long as the starting and the ending products are, the starting and the ending products. It doesn't matter how many steps you go through to get to your ending product. That's fine. So the concept here with our heats of formation is that we can take whatever reactants we have, break them down into raw elements, just absolutely raw elements, and then we recombine those raw elements and form the products. And we've got heats of formation both ways. So we take methane and break it down, combine it with oxygen to make CO2 and H2O. This is the reaction CH4 plus 2O2 to CO2 plus 2H2O, like burning methane. But we have heats of formation for these, right? Here's methane is here, minus 74.8. Right, so let's actually write these out. The methane is minus 74.8 kilojoules per mole. Right, the methane is minus 74.8 kilojoules per mole. CO2 is on here somewhere. CO2, there it is, minus 393.5 kilojoules per mole. Minus 393.5 kilojoules per mole. And the water, minus 285.8 kilojoules per mole. Note that it's liquid water, right? Liquid water. If it was gas phase water, we'd use 241.8 kilojoules per mole. It's different depending on what state it's in. This water is liquid water, so we're going to grab our liquid water, 285.8 kilojoules per mole. 285.8, negative 285.8 kilojoules per mole. And so what we've got is basically a very simple Hess's law problem. And the Hess's law problem goes like this. It's elements. So here's our target, right? CH4, we actually have it up there. So that's our target right here. And we have these three reactions, elements to form CH4, elements to form CO2, and elements to form H2O, because that's what the heats of formation are. It's the raw element thing. So we have these three reactions. We might as well call it 1, 2, and 3, just like we make it a Hess's law problem. And we have those delta H values. Right, this delta H is minus 74.8 kilojoules. This delta H is is minus 393.5 kilojoules, and this one is minus 285.8 kilojoules. All right, so those are our three reactions, which we get from the heats of formation table. Those are our three reactions. This is our target. So we'll do the same kind of concept as we've done for Hess's law, except now we have elements, just these raw elements. So CH4 is on the left side. Right? CH4 is on the left side, but in my thing, it's on the right side. They're all on the right side. It's heats of formation. So that tells me I have to flip this. Right, so I'm going to flip that. CO2 in red. CO2 is on the right side, and there's one of them. Hey, there's one of them on the right side. That one we just keep. We'll keep that one. I'm going to keep that one. And then the H2O in purple. There's two of them, two H2O. Here we just got one H2O. So we're going to have to multiply it by 2. Right, multiply it by 2. And then, so let's do that. Let's flip it. keep that one, multiply it by 2. And we don't have to worry about this because we know that the raw elements are going to cancel out. It'll be fine. It'll just be oxygen, carbon, and hydrogen. And we don't even need to worry about that side of things. We don't need to think about that part. That's why heats of formation is so powerful. So let's actually do that. Let's flip number 1, which would be plus 74.8 kilojoules. We're going to keep number 2 exactly the same, minus 393.5 kilojoules. And we're going to multiply this one times 2 because we're making 2 waters. So 2 times 285.8, 285.8 times 2, 571.6, so minus 571.6 kilojoules. And we're going to add those together. All right, we're going to add them together, so let me just write that in. Add that up, add them together, and we're going to get some kind of number. So 74.8 minus 393.5 minus 571.6, 890.3 kilojoules per mole. 890.3 kilojoules per mole. And that is our delta H of this whole reaction, right? Our delta H of the whole reaction then becomes 890.3 kilojoules per mole. So the concept here is we always have to flip anything on the left side, and we always multiply by the coefficient, and that's it. One way to remember that we have to flip is that it's a heat of formation. We're forming, so we don't flip it where on the side where we're actually forming the product, but on the reactants we're going to have to break it down into its raw elements. So we have to flip the energy because we're turning it into raw elements. So that's our first practice problem. Let's do a second practice problem here. Another way to state it, you do the products, take away the reactants, and you get the overall heat of the reaction. So here we go. Here's C2H6 plus C2H4 to H2 gas. We want the delta H of this reaction. Here's ethane, ethanol, and ethylene. So there's C2H6, here's C2H4. Ethanol is just in the middle, it's not going to get used. So let's write out our heats of formation here. C2H6, we look at our table, minus 84.66, or 68 kilojoules. C2H6 is plus 52.30 kilojoules. Plus 52.30 kilojoules. What about the hydrogen? What about the H2 gas? Well, it's already a raw element. It's already a raw element, so turning it into a raw element doesn't take any energy at all. So 0 kilojoules. By definition, raw elements in standard form have no heat of formation. Okay, so then we flip the reactants, right? So that C2H6 being on the start, it's a heat of formation. So because we're not forming it, we're breaking it up. We're going to have to flip it. It's plus 84.68 kilojoules. And then the products, right? And then the products stay the same. There's only one of them too. So then the total enthalpy is plus 84.68 kilojoules plus 52.30 kilojoules plus 0, technically, because of the hydrogen, and that's equal to whatever that equals, 84.68 plus 52.3, 136.98 kilojoules per mole, and that is the delta H of that reaction. Okay. So the big thing is to remember to flip the reactants. Here everything was just multiplied by 1, so that was fine. We're going to do one more practice problem. Here's one more practice problem. Here is ethanol, oxygen, carbon dioxide, and water. We already know the heat of reaction for one of these, the heat of formation for one of these. Which one do we already know? Well, we already know oxygen. Oxygen because it's a raw element in standard state, 0 kilojoules, right? So by definition, oxygen, any raw element is 0. But we have to find the rest of them. Liquid ethanol, let's find that in our heat of formation table. Ethanol, here it is. Minus 277.7. Minus 277.7 kilojoules. Let's find CO2. CO2 is here, minus 393.5. Minus 393.5 kilojoules. And the water, it's liquid water. We got to keep that in mind. It's liquid water. Liquid water, minus 285.5. Minus 285.5. Oh, wait, 285.8. 285.8? 285.8. Minus 285.8. Okay, now we're going to apply the changes that are based on where they are in the reaction. This is the arrow, that's the reaction arrow. So everything on the left side is not being formed, it's being broken up. Everything on this side is being broken up instead of being formed. And so we have to flip it, right? We have to flip this one, because it's being formed. Plus 277.7 kilojoules, right? Because it's being formed. And the reason we're doing that is because it's a reactant. Okay, it's a reactant, so flip. So flip the reactant. It's being broken up instead of being formed. This one here, the CO2, there's 2 of them. 2 CO2s, so times 2, because 2 CO2. All right, this one times 2 because it's 2 CO2. So we're going to get minus whatever 393.5 times 2 is, 393.5 times 2, minus 787 kilojoules, minus 787 kilojoules, because there's 2 of them. And with the same logic for the water is going to be times 3, because 3H2O times 3 because 3H2O and whatever, because there's 3 of them. So minus 285.8 times 3. 285.8 times 3 minus 857.4 kilojoules. So we've done our kind of Hess's law stuff and adjusted for the numbers and where they are on the reaction on the left or the right. And then what's left is just to add it together. So total, we'll do this in black or in purple. The total here is plus 277.7 kilojoules minus 787 kilojoules minus 857.4 kilojoules, which is equal to some kind of number. So 277.7 minus 787 minus 857.4 minus 1366.7 kilojoules per mole. And that is the solution to our heat of formation problem. That's the heat of formation. That's the heat of combustion here of ethanol. Let me just move that over. Right. So I just took that, and that. Technically that 0 is in there too, but adding 0, taking away 0, multiplying it by 3 is still 0, flipping it is still 0. That doesn't matter. We can just ignore it. We can ignore any raw elements because they're going back to raw elements. So yeah, so that's heats of formation. A very useful thing, right? Much easier than a Hess's law problem because we just have these wonderful tables of heats of formation that we can draw on. Yeah, that's it. We'll be doing practice problems like this in class. Thanks for paying attention, and I'll see you in class. Yeah.